Again, thank you for the kind invitation to speak to you at this symposium today. As already explained, I'm not able to be there in person, but in this particular presentation, I'm going to look at the issue around nitrosamines, looking at it from the perspective of the past, what happened as regards nitrosamines, the present, how we handle nitrosamines as it currently stands, and also as well the future. I must say in all of this, this is a personal perspective and not reflective of any individual organization, although of course, as you're probably well aware of now, I'm an independent consultant with my own organizations, but nevertheless, this is still my own opinions and not that of any other organization. So let's start with what happened as regards nitrosamines. And what am I going to cover here? Well, there's going to be as part of this, there'll be as part of the introduction, I look at the background and the history. And as part of that, I look at the actual impact. What has been the impact of nitrosamines on the pharmaceutical industry for the companies that actually supply the actual medicines, the pharmaceutical companies, to the regulatory authorities like your own within South Korea, and also as well, obviously, the potential impact in terms of patient and access to medicines. I look at the current situation, the risk assessment, how we go about carrying out risk assessments, and as part of that, I'll touch on some or a lot of the collaboration that has indeed been done in this area that's really helped us to be able to move forward in terms of our understanding of risk of nitrosamines and critically in our ability ultimately to be able to control nitrosamines effectively to the limits that are defined for them, i.e. the acceptable intakes. And as part of that aspect of it, I'll talk about relevantly recent developments as far as nitrosamines are concerned, and I'll talk particularly about the carcinogenic potency characterization approach, or CPCA for short, and also as well the enhanced Ames test, the EAT for short. And then finally, I'll talk about what next for nitrosamines. What can we expect to see in terms of ultimately the development of guidance in this area and how effective or otherwise this will be in terms of actually managing the risk associated with nitrosamines. So where did it all start? Well, many of you who are listening to this will be very much aware of this. In June of 2018, Shuanghai, a pharmaceutical manufacturer in China, was informed by one of their customers that there was a new impurity present in the manufacturer's valsartan. They then investigated it, and Shuanghai then sent a letter to all of its customers informing them of the presence of a previously unknown impurity that may have genotoxic potential. And what they did as part of this was they requested immediately that the use of valsartan, the API they'd supplied, would be put on hold. Shuanghai then contacted its customers again, stating that the impurity in question was a nitrosamine. That it was nitrosodimethylamine, NDMA for short, and this was likely to be process related. Almost immediately after this, then we saw the fact that regulatory agencies, this is an example of this as far as the European Medicines Agency is concerned, actually notified, well, everybody really, the general public, certainly pharmaceutical companies through a press release about this contamination. And so this was the start of the issue of nitrosamines. And time doesn't allow me to spend too much time going through the entire history of it and the evolution of this from the risk that we saw with valsartan, the fact that this then became a risk that was associated with all sartans, and then what we saw as part of this was that nitrosamines were seen in other drugs as well that were non-sartans, either through contamination or in specific cases like ranitidine due to a unique reaction, an intermolecular reaction between two molecules of ranitidine to generate the nitrosamine NDMA. Irrespective of that history, the key point is that we saw lots of issues with nitrosamines to the point that led regulators ultimately say we need to understand what the risk of nitrosamines is across all drug substances and also as well all drug products. And ultimately, as far as this is concerned, Because we then triggered these significant investigations, not just for drug substance, but also as well for drug, what we ultimately saw was the evolution of the problem. And what we started to see was the advent of the detection of nitrosamine drug substance related impurities, or NDSRIs for short. And this is illustrated in terms of this particular slide here. So the first issues that we saw with nitrosamines occurred in terms of the first issue being with NDMA and NDEA, being seen in sartans in 2018. And then what we saw was the regulatory agencies essentially make the request for a portfolio risk assessment, i.e. all drugs, small molecules and biologics. Applicants were asked to assess the risk of nitrosamines within all of their portfolio. And FDA followed suit as well, and other regulatory authorities clearly have as well. And ultimately, we went through a series of deadlines. Now, I'm not wanting to discuss those in detail. The point I really want to make is that by looking as part of these risk assessments to both the drug substance and the drug product, what we saw in these risk assessments was the advent of nitrosamine drug substance related impurities. The first issue associated with the simple dialkyl nitrosamines seen in valsartan relating to the chemistry. These formed during the drug substance manufacturing process, a process and a risk that we now understand very, very well. However, by looking at the drug product, what we saw was we start to see these other nitrosamines, these NDSRIs, nitrosamine drug substance related impurities, like this example here, nitroso and allopril. And unlike the simple dialkyl nitrosamines that were process related, in this particular case, these NDSRIs form largely within the drug product. So what's the problem? What's the issue with having these new classes of nitrosamines? Well, in terms of the nitrosamines, the NDSRIs specifically, there is a significant issue associated with this. Generally, when we're talking about things that are of concern for immunogenicity, the way we address them, and as written within ATCMC, is to carry out the AIMS test. This is the bacterial reverse mutation test, and it's used to assess the mutagenicity of chemicals. And this is written into ATCMC. And indeed, if you were to get a negative result as regards this, then it's justified that the compound that was being tested, including these nitrosamines, the NDSRIs, would be justified as being of no significant risk in the context of ATCMC. However, when we started to look in more detail at this, regulators start to have concerns over the validity of the AIMS test, and indeed whether the AIMS test as it stood was suitable for being able to assess the mutagenicity of an NDSRI, of a nitrosamine drug substance related impurities. And indeed, if we can't therefore mitigate the risk by carrying out an AIMS test, then the only option available is to test the actual levels. But test to what level? Because unlike the simple dialkyl nitrosamines, NDSRIs, nitrosamine drug substance related impurities, have limited or no calc data. So what is the limit? Well, the limit that was chosen in many cases was simply to read across from the data that we had, which was on simple dialkyl nitrosamines like NDMA and NDEA, and the extreme low limits associated with those, and apply those to these NDSRIs as well. The ultimate consequence of this was it enforced the need to control to nanogram limits, detect down to parts per billion, and essentially it proved to be impossible to manufacture many medicines to these limits. As we started to address this particular challenge and all of the implications that went with this, both industry and regulators published a lot of material over a period of about 5 to 6 years. And this included presenting a regulatory context, i.e. where nitrosamines had been seen as a risk and what were the potential sources of those risks, either the nitrosamines or perhaps precursors to nitrosamines. So this culminated in a couple of papers. The Horn et al. Paper that was published by Health Canada, led by Stephen Horn, and the Rob Bream from the European Medicines Agency, who published the European Medicines Agency's reflections on this issue. Both these papers are very much worthwhile reading if you've not read them previously. And similarly, from an industry point of view, we wanted ourselves to actually define what we saw ultimately as the risk sources. And so we saw again really key seminal publications like the landscape paper from York Shingleman. This provides a really good overview of the extent of the risk, particularly in terms of the NDSRIs. There's the Saga paper. This talks about the progress that's been made in managing the risk associated with nitrosamines. If you've not read them and you want to go into more detail, I would suggest you read these papers. They are well worth actually studying. But just to give an overview of the narrative as regards this, and ultimately what the key challenges were, was the Saga paper made it clear, unfortunately, what that paper showed was that even if you're talking about 1 or below 1 part per million of nitrate in, for instance, an excipient used within the drug product, then that is more than enough to create concerning amounts of the nitrosamine in the drug product. And that indeed limits like 18 nanograms per day, which was the conservative read across from a simple dialkyl nitrosamine to set limits for NDSRIs, that those kind of limits were not achievable. Indeed, in many cases, not only was it not achievable to control to these limits, it wasn't even possible within the drug product to be able to detect down to those limits, depending on factors like the dose and other factors. One of the other challenges with this as well was that if 18 nanograms per day is not technically feasible, then one of the approaches that was suggested at least was use the actual specific data for an individual nitrosamine and look, for instance, at read across to others where there is more significant carcinogenicity data and define a limit based on those surrogates. Well, this was something that was extremely difficult to do. And in the absence of that, we had to apply limits like 18 nanograms per day. And if those limits were applied, then corrective actions and preventive actions and even remediation, even if possible, would have taken several years. And could we wait several years whilst all the medicines impacted by this would face the uncertainty as to whether or not they could be still continue to provide it to patients? Well, the answer to that is effectively no, we couldn't. And indeed, this even assumes we could do the analytical testing, either to develop the methods, get the limit of detection, or even have the capacity in terms of the equipment needed to do these kinds of analysis, which is very much high-end, high-cost mass spectrometry, and requires very specialist skills. And just to very quickly illustrate the point about the challenge that was faced, at least from one element of this, which is around sensitivity. How sensitive did these methods need to be? Well, depending on factors like the acceptable intake and the maximum daily dose, certainly if you're looking at limits like 18 nanograms per day, which for a number of medicines, organizations were faced with limits like this, then you're very much into a red zone of having to have a limit of detection below 1 part per billion, which is incredibly difficult to do. So what was needed? Well, what was needed was, well, before I even say that, the reality was this presented a crisis. Thousands of medicines were a threat in critical areas like heart disease, where several of the critical drug classes were at risk associated with this. So what was needed, bearing in mind this was a crisis? Well, we needed to maintain the benefit risk calculations on this. These medicines are critical to be and vital to people's survival and their overall health and well-being. We needed to balance the risk associated with nitrosamines against the benefit from taking those medicines. And also as well, we need to get global alignment. This would include all the major regulatory authorities and territories outside of that. Clearly, of course, including South Korea in that scenario. And the reality was, without some changes, we faced a crisis and an inability to maintain the supply of products that contain these structurally complex NDSRIs, nitrosamine drug substance-related impurities. So what was the way forward? Well, I've already said, that defining an acceptable intake based on, for instance, read across and structural similarity to a molecule for which there is mutagenicity or carcinogenicity data, that there was a bottleneck associated with that. In a meeting with the regulatory authorities, May, June of 2023 said, we've got a huge backlog. We've got 60 NDSRIs that require assessment at the moment. Something had to change. We had to find some way of being able to address the crisis. And what happened was the regulators came up with a proposal of a carcinogenic potency characterization approach, or CBCA for short. And the critical thing is that it doesn't require detailed actual data in terms of carcinogenicity data or mutagenicity data, that it could actually be done based on the structure of the nitrosamine. And based on that structure, you could define an acceptable. And in terms of the actual limits that are defined within that categorization approach, there are 5 potency categories, and they range from the most potent with a limit of 18 nanograms per day through to 100, 400, and 1500, and a 5th category of 1500 still, but this is where you may have, for instance, actual safety data, for instance, the result of a revised Ames test. How do we do this? How do we calculate those limits? Well, I've said it's based on structure. And what it's based on ultimately is structure as it relates to the nitrosamine, and in particular, what would happen to the nitrosamine once it was inside your body. And the reality is that nitrosamines require metabolic activation to ultimately form the mutagenic species. The mutagenic species from a nitrosamine is a diazonium ion. And to form the diazonium ion, which is obviously of concern, in vivo, what has to happen is you need metabolic activation of the nitrosamine. In particular, what you see is removal of a proton in this alpha position to the nitrosamine group. You remove it and you replace it with a hydroxyl group. And what happens is that rearranges, kicks out an aldehyde, forms a diazo hydroxide, which then reacts further, eliminates water and forms the diazonium ion. And that is the potential mutagen carcinogen as regards this. So if that's the mechanism, then we can relate that mechanism to some form of structural assessment to define the potency. And that's exactly what the CBC categorization does. It does exactly what I've just described. It looks at this in the context of, it applies an empirical model that relates to the mechanism of action of nitrosamines, and ultimately this is tied to the actual number of protons on the alpha carbon. So depending on the number of protons on the alpha carbon, this describes how easy or difficult it is to hydroxylate in that position and ultimately create that pathway to the diazonium ion. So the score is based on the number of protons. And as you can see examples here where you have hindrance on one side, but protons available on the other, that can still undertake that metabolic activation. You can get hydroxylation, but of course it's more sterically hindered. And clearly you can't get the abstraction of a proton and hydroxylation in that position there. It's blocked. There is no protons available. So that's given a higher score. And the higher the score, the lower the potency. The more protons that are available, the higher the potency. And so from that point of view, you start off by doing this count. How many protons do I have on either side in proximity to that nitrosyl group? And so you can do that, and then ultimately that's your start point, and then you adjust for activating and deactivating features. And there are a number of features that lead to the deactivation of an N-Nitrosamine that make it less potent. They include things like carboxylic acids, small ring systems like a pyrrolidine, and a number of other factors. Also as well, we have some factors that cause activation. These are just a couple of them listed here. So you go through your actual system or your and you score it. And this is an example here of a nitrosamine, N-nitrosomeropenem. In this case, you do the alpha hydrogen count. You get a count of 1 on one side, 2 on the other. So it's a 1-2 system, scores 3. It's a carboxylic acid, deactivating, so +3. It contains a pyrrolidine ring, which again is a deactivating feature. And also as well, there is this electron withdrawing group on one side of the ring, and so that also gets scored. And so you calculate the overall score. It gives you a score of 10. Anything over 4 or more will place you into category 4 and an acceptable intake of 1500. So this was a really, really big step forward. This suddenly turned the impossible into the possible in terms of firstly setting a limit and secondly being able to control to an appropriate limit. And this is illustrated here on this particular slide. Up to 40% of all drugs are secondary amines and therefore have the risk of forming a nitrosamine. And within that, 30% of all impurities that exist either in the drugs that are secondary amines or tertiary amines, or even in some cases within drugs that are neither of those things, still 30% of those impurities could be a secondary amine. In reality, what we found was that this encompasses thousands and thousands of molecules, but by applying the CPCA, ultimately 66% of the secondary amines now move from, instead of applying a limit of 18 nanograms per day, which was the default, they have a limit of 1500 nanograms per day. And from that point of view, being able to actually control the level of a nitrosamine suddenly becomes possible to detect it, and even more importantly, possible to control to as well as the carcinogenicity potency characterization approach, the CPCA. At the same time, because of the concerns previously around the standard Ames test, it became necessary to develop a revised Ames test or an enhanced Ames test, or for short, the EAT. Now this is essentially the standard Ames test, but in this particular case it now uses 2 activating agents. So the bacteria that we carry the Ames test out using, they cannot actually undertake the metabolism I've previously described. They're incapable of doing that. So you have to assist the bacteria. You have to use liver homogenates and activating agents that will actually promote the metabolism I've described. And they use something called rat S9 and hamster S9. These are essentially liver homogenates taken from animals that have been exposed to chemicals that overproduce these enzymes. Many companies previously used rat and hamster. The big change with the enhanced Ames test is the level and the amount of these activating agents that you need to add. It's now being recommended using 30% rather than the standard 10%. In many ways to upregulate the Ames test and make it more sensitive to nitrosamines. You also, as it says here, need to include 2 nitrosamines that are known to be mutagenic. This is to check that the test is working. But even then, we don't necessarily get to a position where we are able to, certainly not to be able to say that a negative Ames, a negative EAT is enough to address the risk associated with nitrosamines. The CPCA has been fully adopted, but in terms of how you interpret the enhanced Ames test, it's different. In Europe, if you run the test, the standard test, as is the way it's described, and you get a negative, in Europe, that will allow you to set an acceptable intake of 1500 nanograms per day. It goes into that CPC category 5. The FDA position is different. A negative result in a validated Ames test, the FDA say, may be used to support a high limit for an NDSRI. However, manufacturers and applicants should note the FDA may request additional safety data beyond the enhanced Ames test to support an alternative acceptable intake. So this is quite a difference in the position. And the Ames test is an in vitro test. You can use in vivo studies. In Europe, you can use, for instance, a transgenic study in mice or rats. And if it's negative in that test, then the limit that would you apply to that nitrosamine would be Q3A, Q3B limits. But the FDA documents currently make no reference to this, and they certainly don't allow control to Q3A, Q3B. And so from that point of view, we don't have consistency in terms of how the enhanced aims test will be interpreted, and certainly not how the results from further testing, for instance in vivo testing itself, would be incorporated into an overall risk assessment and a decision made on. One of the other things is that for nitrosamine, it isn't just about the limits, it's also, of course, what is the risk of having a nitrosamine formed and being present. And so you carry out, and indeed one of the places you can even start with the risk assessment is, do I even form a nitrosamine? Not all amines can lead to a nitrosamine. In fact, some nitrosamines, or some secondary amines, for example, won't form a nitrosamine. They may be complex molecules that have other reactive sites. You try to form a nitrosamine and you may get different things happening. In this particular case, you see nitrosation does occur, but that intermediate very quickly rearranges. It's called a Fischer-Hepp reaction, and that nitro group ends up actually on the aromatic ring. That's not a concern. You may even see that nitrosation or nitration occurs actually on part of the molecule, not even related to the nitrosamine or the risk of forming nitrosamine. So one of the questions you ask is, could my nitrosamine even form? That's one of the you ask. And one of the things we want to do is ultimately be able to carry out a systematic risk assessment process to be able to actually construct a workflow and comprehensive guidance to be able to actually explain how to and ultimately systematically assess the risk associated with nitrosamines, starting with the drug substance manufacturing process, the reagents, solvents, catalysts, chemical processes that were involved. What would be the risk of forming a nitrosamine in the drug substance? Subsequently looking in the actual formulated product as well. For instance, within excipients, do they contain nitrites that are a potential nitrosating agent, at least in the presence of water? So what has happened from a industry perspective is the Trade Association in Europe, EFPIA, have developed this systematic process. And this process I would very much recommend that you actually look to do and use for your risk assessments if indeed you are conducting these yourself. Look at these workflows. They are based on risks that have been reported by authorities from the experiences the industry have seen following root cause investigations and critically as well science studies. And what we know about nitrosamines is this critical point. To form a nitrosamine, you need three factors. We refer to this as the nitrosamine triangle. To form a nitrosamine, you need a vulnerable amine. You need a nitrosating agent. And the third factor is you need conditions that would promote the formation of a nitrosamine. If any of these are not present, you may not form a nitrosamine. And there is this systematic process that's been described for doing this. Time will not permit me to actually train you in how you actually go through each of those steps. But what I would point out is, as regards this, is the process is a risk assessment process consistent with ICH Q9 and the principles within that. You start off with a hazard assessment, hazard identification. Can I form a nitrosamine, or is there a nitrosamine that might be present as a contaminant? The risk evaluation. What category does it belong to in terms of the CPCA? And critically, what level may be formed, either modeled or actually measured? Then it's the risk analysis. This is my level of nitrosamine I formed. This is my acceptable intake. How do they compare? And ultimately, from all of those factors, you look to risk control. Do I have a nitrosamine risk? If I have, do I need to control it? Do I need to routinely test for it? Or do I even need to change my process or my formulation to control it? We know that back to that triangle, that actually the two of the three key elements are vulnerable amines and a nitrosating agent. We know where these risks may arise. Amines may come in, for instance, from solvents, reagents, or starter materials, or impurities, or any of these sources. There may be API degradants or API impurities. They may even arise from excipients or drug product degradants. But what about the other side of that triangle? What about the nitrosating agents? In theory, they could come from water, although I'll come back to that in a moment. The deliberate use of nitrosating agents. Again, API degradants or species, reactive species in the air, referred to as NOx, or excipients. Well, we know that nitrites can be found in excipients. But what do we know about each of these risks, and what are the key factors associated? Well, it's very common to see vulnerable amines at least at trace levels, or see drugs at secondary amines. We know that trace nitrosating agents are present, particularly in reagents in the synthesis, but even more so within the formulated product within the excipients. What we also know is, and what's less common, is the deliberate use of nitrosating agents, certainly in the API, the drug substance manufacturing process. And we can protect the drug substance from other reactive species in the air, these NOx species, by running processes under nitrogen free. And again, extending this further to the drug product, we can similarly identify where these risks come from. I'm not going to repeat what I've just said in terms of what was largely covered on the previous slide, but one thing I will say is that although secondary amines and tertiary amines are a risk in the drug substance, in terms of the drug product, where you're talking typically about solid formulation, tertiary amines react so slowly with a nitrosating agent that they are not a risk within the formulated product, unless it's an activated tertiary amine, which is not that common. And again, as we've done, as far as the drug substance is concerned, again, we've been able to build these workflows, this time for the formulation process and the finished product and the packaged product, and even take into consideration the finished product at the end of shelf life. Could a nitrosamine form over the time that the drug product is stored? Again, we'll be able to refer to lots of work that's been done over the last 5 or 6 years in relation to the formulation and the packaging, to the modeling and the use of predictive models, how we can use wet chemistry to predict what would happen actually within the solid phase, the use of the enhanced Ames test, and all of these things. All of these, whether you're talking about the drug product or the drug substance, all relate to this triangle, the fire triangle or nitrosamine triangle in this case. Do I have a vulnerable amine? That could well be your drug itself. Do I have a nitrosating agent? Well, in a formulated product, you have nitrites and excipients. So yes, we certainly have that as a risk factor. And again, the question of the conditions. This is reflected in, again, a workflow. This has been published through the European Trade Association and is available for you to use. And I've already said I would recommend using it. In very simple terms, what might this kind of look like in practice? Well, one of the things I would always advise is follow that process. Do I identify a potential risk of a nitrosamine? If I do, I next perhaps would try to make it. Could it even form? If I can't form it, it's not a risk. Either from the point of view of that, I haven't got a reference standard, but also as well from the perspective of it's not a risk critically, because if I can't form it under extreme conditions, it won't form in your body. If I do form it and I can run the risk of it actually forming in vivo, the next thing is to model it. I'll come back and more on that in a moment. Or if we model it and it's a risk, reduce the level of one of the factors. The most obvious one is reduce the potential risk associated with a nitrosating agent. In the formulated product, the level of nitrite within my drug product. Another thing is, if I still have a risk, is consider scavengers. Adding something to your tablet to control or at least look to prohibit the formation of the nitrosamine. And if all of these things don't work, then there are other safety tests we can carry out, particularly, well, both in vitro. To this point about, can I form a nitrosamine? This paper has been published, which looks at providing 3 separate methods by which you can try to form a nitrosamine. If it's negative on all of these, then it's no risk. Bearing in mind these are extreme conditions, you're using 1,000,000 times higher level of nitrites than you would certainly, or you would see in a formulated product where you may have 1 or 2 ppm of nitrite within the actual excipient and therefore in your product. There are 3 sets of conditions. 2 of them are aqueous, 1 is inorganic. If you can't form a nitrosamine under those, then they're not a risk. So that's always a very point. We also know a lot about nitrosamine chemistry, and not because of what happened with valsartan and subsequently, but actually because we've known about the risk of generating nitrosamines for a long period of time. Nitrous acid is not a nitrosating agent. If you take nitrite, dissolve it actually in water, you'll form nitrous acid, an unstable acid. But even that is not the nitrosating agent. It must react with something else. Perhaps it will react, for instance, with another mole of nitrous acid, in which case you may see these kind of species. Under high acidity, you may just get the nitrosyl cation, or you can get catalyzation through also reacting with another nucleophile, like a chloride ion, to form this nitrosyl chloride reagent. But the key thing is we can understand what will form, under what conditions, and critically, how much it will react with a secondary amine and what levels of a nitrosamine you will form, all based on chemistry carried out many, many years ago. And in terms of brought up to date, in terms of the risk in the current situation in this more recent publication in 2020, led by one of the things we thought was a risk was water. Nitrite is actually known to be in water, but how much in reality? The WHO, the World Health Organization standard for level of nitrite in water is 3 parts per million. But we know the typical levels are much lower than that. And most critically, most recent work has shown that the levels are even lower, that even in drinking water, the level is around 1 part per billion. And that even then, that's the method limit of quantification. And in purified water, it's even lower, another order of magnitude. So to the question, is this an issue when you're thinking about formation of nitrosamines in a drug substance manufacturing process? And the answer to that is a straightforward no. At these kind of levels, it is not sufficient to generate levels of nitrosamines of concern. So with our scientific understanding, we can rule water out as a potential source. But just to give you an example of how we would go through this process. So this is a nitrosamine that can form. This nitrosamine results from, this is a secondary amine drug, a beta blocker used in the treatment of heart disease. You can form a nitrosamine, and the risk is that you would form that nitrosamine on storage. So what can we do? Well, we know a lot about the chemistry, both from a wet chemistry perspective, and we can use that to model this within a dry formulated product. You can run the model, and it suggests you form 2,300 nanograms of the nitrosamine at the maximum daily dose of that beta blocker, the highest strength. And that's all based on, for instance, the level of nitrites within the excipients that are used in the formulation. This is actually significantly less than the theoretical maximum, because this model does take into consideration factors like the amount of water present, the pKa, the pH of the formulation. So it's fairly realistic in this respect. But the point is that it is still conservative, but nevertheless, because of the fact you're above the acceptable intake based on the CPC category of this case for 1,500 nanograms per day, I have to develop an analytic. And what did this show? Well, what this showed was that when you actually tested the product, the level of that nitrosamine, the nitrosamine of this beta blocker, was less than the acceptable intake, even though it increased over the time that the product was stored. And these are different formulations with different concentrations. But the key point is that's the acceptable intake. This is predicted to be the level you could actually form and how it relates to time. And this is the reality, the levels are much lower. So my recommendation is to find out, would I actually achieve or see a level that exceeds the acceptable intake using this model? If you don't, then, and you were predicted to be below the acceptable intake, it's a conservative model as demonstrated by this against the actual levels that were measured. So part of a risk assessment could be simply to carry out these calculations, do this predictive model, and if you're below the AI acceptable intake at the end of the shelf life, then I may not require any analytical testing. The model, as I've said, over predicts against the observed, so it's a very useful. I said that we know that we see nitrites in excipients, and we see quite a lot of variation. These are different excipient suppliers for the same material, for microcrystalline cellulose, and you can see how the levels actually vary depending on the supplier, not just in terms of the typical levels depending on the supplier, but also the spread within even the same materials supplied by the same excipient manufacturer. The critical question is, how does this matter, and how does, well, this is the nitrite results for 8 common excipients. Excipients like cross-povidone, microcrystalline cellulose, cornstarch, lactose, those kind of things. And you can see from this the level of nitrite is quite different depending on the excipient. But actually, the true risk relates to what is the actual contribution of nitrite to the overall drug product. And if you look at it from that point of view, that some of the excipients like microcrystalline cellulose or cornstarch or others like that, they actually are used at relatively high levels in the formulated product. You may have 50% of your product may, for instance, be lactose. So the level of nitrite in those, in some ways, more critical than it is in contributions that come from excipients used in much lower levels. So we can look at, in effect, that normalized contribution to the drug product. And if we understand that and tie it to the model, we know what level of nitrite would be problematic, what level we would expect to see in our excipients, and critically, what level may I need to control down to. And so from that point of view, we can know what is and isn't a risk. Another key point on this is that if I'm doing that, I model it. I may, for instance, then decide to change the supplier, at least of an excipient. I remodel it. It still suggests I have a problem. I may have even analytical data that says my level of nitrosamine is too high. Well, one of the things you can do is, and has been studied, is this whole idea of adding a molecule to your formulation or your manufacturing process that will inhibit the formation of a nitrosamine. This is one paper. There are several others. They've shown, for instance, that these amino acids will prohibit the formation of a nitrosamine actually within formulated product. And what they show is the extent of inhibition of the formation. So we can use these added to, for instance, the manufacturing process and solution. We can add them to the solid solid dose form as well. This is an example secondary amine coming in various forms, including the hydrochloride salt. This was mixed with several different types of scavenger, and depending on the amount of the scavenger that's added, you see that you can get, certainly for the high loadings, like 1% of the secondary amine, then you see significant inhibition of the formation of the nitrosamine. Great, you may think. Isn't that really good news? But what's the reality? Scavengers are not quite as simple as you would hope. All of the scavengers that were looked at in solution in one of those studies I described actually lowered the level of the nitrosamine in the solution. That's great. However, what we found was that in the solid it was a little bit more challenging, and that only certain excipients and additives would reduce or eliminate the level of nitrosamine. Other critical point on this is that you can't predict. You can't say, this is my secondary amine, therefore I will use, for instance, ascorbic acid, or I'll use L-cysteine based on that structure. It doesn't work like that. Each scavenger is tried from a case-by-case perspective. And then you do the full-blown experiments, you develop the actual formulation and the tablets, and then you put them effectively on instability, and you look at the effect of those different scavengers in regards to that. And what you find is that depending on the drug itself, whether it and these all show very similar behavior, is they show inhibition of the formation of the nitrosamine, but you get this discoloration. You see these tablets that are now highly colored. That obviously would not be acceptable to patients. So from that point of view, using problematic. And to make the challenge even more complicated, we know that we now see also as well the formation of nitrosamines because of the presence of certain NOx species in the air, like N2O4, N2O3. And what these will do is they will actually react with a secondary amine to form a nitrosamine. What we do know is that there's little evidence of this happening, but where it has been published, there's a clear evidence that nitrosation through NOx species. And indeed, a recent publication in 2023 showed that this was the drug metformin. Metformin contains dimethylamine as an impurity within it. That dimethylamine actually can nitrosate, depending on, for instance, the level of NOx species in the air. And in this particular case, the metformin that was manufactured at one site, Yamagata, which is in rural Japan, had levels of the nitrosamine NDMA at much lower levels than the levels of NDMA at a second site, which was a site in a more industrial space, where the levels of NDMA formed were much higher. And in those cases, what you can see is there's a very clear correlation. For instance, the level of of NO2 in Yamagata is much lower than the level of NO2 for the same process where the manufacture takes place at Osaka. And there's a clear correlation between the two. The higher the NOx species, the NO2, the higher the level of the NDMA, the nitrosamine within my drug product. It clearly is related. So I'm conscious of the time and coming literally to the last slide in my presentation. So where nitrosamines? Well, where we go next is we're developing an ICH guideline covering nitrosamines, or to be more precise, an addendum to the existing M7 guidance on mutagenic impurities. And this will focus on nitrosamines. We know, as it currently stands, that being able to apply the carcinogenicity potency characterization approach, a good level of control over the issue of nitrosamines has been possible in existing products, but it's not perfect, and we know and see still significant challenges. And so there are a number of key areas that the guidance will have to address. For instance, can you apply durational limits to these NDSRIs? What you can to a mutagenic carcinogen, small molecule. So does the same apply? What about the use, for instance, of modeling? Can you model this and will regulators accept that the models are a worst case scenario? Can you support them with purge calculation to say, well, if this secondary amine came in here, 3 steps down the process, I would have purged it. So if that's the case, why am I worried about trace levels of that secondary amine in the drug substance? Scavengers, can we make that whole process of defining a scavenger more predictable? The balance in terms of safety testing, when or where if to move from in vitro to in vivo, but also a lot of exciting work looking at some new and novel both in vitro and in vivo tests at the moment. And so all of these things are really important, all moving forward at a rapid pace. So the point that I'm ultimately making here is we've got to a good place with nitrosamines. We know we can control them generally using the CPC categorization. But equally as well, we know that there are cases where the nitrosamines, we know that particularly if they are of category 1 or category 2, are going to be problematic to control to those limits. So it's really important that we have a systematic process, and we also have the ability to make changes to processes or add a scavenger to find ways and means of controlling nitrosamines ultimately. I'm optimistic. I hope the addendum will be a real step forward in regards to this. And as I say, I'm keeping my fingers crossed and I'm hopeful that will truly be the case. But we'll have to see. Despite that and the uncertainties, I'd just like to say I hope you found this useful. Thank you again for the invitation, and sorry I can't be there in person, but I hope you enjoyed it and it's been useful to you. And so with that, I'll say thank you very much. Thank you.